Applications of the ideal gas law. So the last video we talked about how to use the ideal gas law, PV equals nRT, for calculation purposes. Now we're going to add to that. So gas density and molar mass. So once again, we know our, change the color here. We know our ideal gas law is PV equals nRT. Now, if we wanted to solve for density, density equals PM over RT. We know P is pressure, R is their gas constant, T is temperature, and M here is molar mass. And we know molar mass has units of grams per mole. Also, remember, density, we're going to use the units grams per liter in this case. Grams per liter. Okay, so the first problem says, calculate the density of nitrogen gas at STP. So we're going to use this formula here. So D equals PMRT. So our density equals our pressure, it says is at STP. So we'll make it easy on ourselves. We'll say it's 1 atm. Now nitrogen gas, remember nitrogen is diatomic, so it's N2. So we have 14.01 times 2. So our molar mass will be 28.02. Now our gas constant, since it's going to be an atm, and I'm not sure why this is sideways. Write that for you. So we will use 0.08206. Now, temperature, since it's at STP, so it's 273.15. So now, D equals, since 1 times anything is the same number, so we have 28.02 divided by 0.08206 times 273.15. And we get 22.41. So we divide these two numbers. And we get 1.25 grams per liter. Okay. Now, we have a few examples of this because this is new. So it says calculate the density of nitrogen gas at 25 degrees Celsius and at a pressure of 872 torr. All right. So, first thing, we know our equation. D equals PM all over RT. So now, pressure. It's at 872 torr. And I'm going to make it easy on ourselves. We're going to change those to atmospheres. So 872 torr times 1 atm all over 760 torr. So 872 divided by 760. And we get 1.15 atm. So this will go here. So D equals 1.15 atm. Now, molar mass we solved in the previous problem, so 28.02 because we're still using nitrogen gas. Our R value, we will use 0.08206. And our temperature will be 25 degrees Celsius, but we have to change that to Kelvin, so plus 273.15. So it'll be 298.15. So we'll have 32.223 on top, and on the bottom we'll have 24.47. So our density will be 1.32 grams per liter. Okay, so now a sample of gas at 300 Kelvin has a mass of 14.5 grams. Calculate the molar mass of this gas if confined in a 3-liter tank at a pressure of 650 millimeters of mercury. All right, so this is what we're going to do first. Now we could use our normal ideal gas law. We're not looking for density. So, PV equals nRT. Remember, it's a lot easier to write out your formula so you see what variables you're working with and you know if you need to convert something or not. So, pressure, 650 millimeters of mercury. I'm going to change those to ATM. So 1 ATM all over 760 millimeters of mercury. So I get 650 divided by 760, and I get 0.86 ATMs. So we have 0.86, we have a volume of 3 liters, equals, now we want to solve for molar mass, and we know the units for molar mass are grams per mole. So we already have the grams part here, as it says in the problem, the 14.5, so we're going to leave this till the end, so we need to calculate for moles. So N, since our pressure is in ATM, we're going to use 0.08206. And then we're going to multiply that by 300 Kelvin. So 0.86 times 3, we get 2.58 equals 0.08206. And we get 24.62 N. So we'll divide both sides by 24.62. And our N value, we get 0.1048 moles. So now we have 14.5 grams divided by 0.1048 moles. So we divide these two numbers, and we'll get our molar mass. And we get around 138.36 grams per mole. So one more example. So it says calculate the molar mass of a gas that has a density of 1.48 grams per liter at 40 degrees Celsius and a pressure of 125 kPa. So now we know density, so we're going to use that density formula. So we know D equals PM all over RT. So density we know is 1.48 equals our pressure, 125 kPa. We'll leave it in kPa. We'll just use the R value for kPa. We're looking for molar mass, so that is our variable, all over 8.3145 times 273.15 plus 40 is 313.15. Okay, so now we are going to multiply, cross multiply and divide here. So we're going to multiply 1.48 by 8.3145 and 313.15. So we get 3,853.45 equals 125 capital M. So if we divide both sides by 125, we're going to get a molar mass of 30.83 grams per mole. Now, so we learned two different applications of the ideal gas law. We learned how to calculate density, molar mass, and now we're going to use actually some gas stoichiometry using the ideal gas law. Okay, so we just have one problem here. It says the following reaction takes place at 1 atm and a temperature of 298 Kelvin. And we have the decomposition of calcium carbonate. So how many grams of calcium carbonate will be needed to form .29 liters of CO2. So the first thing we need to do here is we need to use our ideal gas law, PV equals nRT, for the value given for CO2. So this 4.29 liters is what we're going to use in our ideal gas law. So what we're going to do, PV equals nRT. So it tells us our pressure is 1 atm, our volume is 4.29. Number of moles, that's what we're trying to find because we want to go from moles of CO2 to grams of CaCO3. So, gas constant 0.08206 because our pressure unit is in ATMs. Temperature 298. So we have 4.29 equals divide both sides by 24.45. And N will equal 0.18 moles of CO2. So I'm going to erase this because I don't have a lot of room. So remember 0.18 moles of CO2. So now we're at 0.18 moles of CO2. So 0.18 moles of CO2. Since we're in moles, right, our easy pass station, we want to go ahead and go over the bridge, so we need our mole ratio. So it'll be 1 mole of CaCO3 all over 1 mole of CO2. Moles of CO2 are gone. We want to calculate the molar mass of CaCO3. And our molar mass is 100.09 grams of CaCO3. So now, last part, 0.18 times 100.09, and we get 18.02 grams of CaCO3. And this concludes our video on applications of the ideal gas law.